So 6.1, exponent rules, exponent stuff. Now radical expressions and functions. There's a reason why we're doing this here immediately after exponent stuff. It just probably won't become so clear until we get to 6.3. So radical expressions, that's another name for radicals is roots. So this would be a math root right there, specifically a square root. If we give it an index of 3, and then it's a cube root. Anything beyond 3 of those, just its own root. So if you saw something like this, we don't have a special name for that in math. You can create your own if you get nerdy enough, and people may respect you for it. Just write your doctoral thesis on it, and you can give talks about why it's a 4 and why you named it what you did. But for now, this is just the 4th root. I know you're planning on it, right? No. Radicals, roots. Yeah, so there we go. Square roots. Again, they're not going to show this. This is what we call an index right there, right? The n is an index. If it's not shown, it's not a phantom 1 anymore, and this is where it causes confusion. It's a 2. Because the square has 2 dimensions. So that's one way to remember. I don't know how you're going to remember it, but that's how I remember it. So there you go. But again, they're not going to show that 2 right there, so don't expect it to be shown. You do need to know that it is there. It's a phantom 2. It's the only phantom 2 that I'm aware of. There's phantom 1s and phantom 0s. Now you see a phantom 2, and you can rejoice. But cube roots have the 3 because cubes are 3-dimensional. All the roots, like again, if you have a number there, let's put something in there that's like an 8 right there. This, again, it would just be the 8th root. Okay, it's its own root. A little bit of vocabulary is the radical is the actual symbol for the root. And then the value that's on the inside is called a radicand. So if you really badly want to look nerdy in front of people, just start using this vocabulary. It works. It works. Just, if you're in junior high, then you might get beat up, which we don't want. Perfect squares and square roots. So we did ask you guys to memorize the first 12 perfect squares. Some of you guys were like, I never will. And that's fine, I get it, because your calculator has it memorized. But if you can memorize these, things go a lot faster, especially with square roots. So if you take these perfect squares, that's this purple list right here, and square root them, then you get back to the actual bases that were there. These 1, 2, 3, 4, all the way to 12. Of course, there's more. It'd be nice if you could memorize all 12 of these. But most students don't. And sometimes they use profanity when they tell me that they're not going to. Either way, I don't really care. Just if you can, you're going to help yourself out. If you're not, use a calculator. Please use a calculator. I really don't care about the cube roots because if I see those, then I'm going to the calculator, or I'm going to simplify these a different way. All right. So radicals, the principal, negative, square roots. So square roots generally have two values that can multiply to get us that number. So if you see a square root like this one right here, right, the square root of 4. Here's your question on that. What number times itself is 4? Now, of course, that is 2, because that is our primary root. The other would be negative 2. Negative 2 times negative 2 is 4, positive 4. And we've seen this before. If you take the square root of something that's negative, again, this would be what times itself is negative 4. There's nothing times itself that's negative 4 yet. And so in the past, we just said that's not real. Fair enough, okay? But right now, when we find these square roots, we're just looking for the positive value there, unless it asks specifically for all the square roots. If a negative's out in front, so see the difference here. The negative on the inside is part of the radicand. So there's your nerdy vocabulary for today. Then it's not real, right? This one would be not real. But if the negative were on the outside, that's okay. So if you had the negative square root of 9, you can get something out of that. That'd be negative 3, okay? Now, this is just really an order of operations thing. What's the square root of 9 is 3, and then apply the negative. Boom, there you go. In fact, just to kind of expand on what we're going to be seeing, it's really negative 1 times the square root of 9, which would be negative 1 times 3, which is negative 3. I don't know if that helps. Again, it's kind of this order of operations thing. But for even roots, the radicand must be positive. So that's the inside of the radical there. And that's if you have an even index, like a square root. If a is not a perfect square, the square root of a is an irrational number, but we can show those irrational numbers in a much prettier way. For example, if I said, what's the square root of 5? Now you could put this in the calculator and say square root of 5, enter, and it says it's the square root of 5, but the decimal itself, it says is 2.236067978. And as ugly as that is, it actually goes on forever and never repeats or terminates, which is why it's called irrational, if you care. You know, so rounded, yeah, you could make it 2.24, but really, we would just want to see it like this because it's much prettier. You know, if you want to, whatever, right? It'll tell us if it wants the decimal or the square root simplified. All right, the square root, the number m is the square root of n if m squared equals n. Oh, geez. Okay, so m is the square root of n. Here's what it's saying. This actually goes back to principles of equality. Is if you were to square root both sides right here, you end up with m equals the square root of n. So, as it turns out, principles of equality are not limited to addition, subtraction, multiplication, and division, which we know have their purposes, right? We use addition and subtraction to create zeros, which we make phantom zeros. We use multiplication and division to make phantom ones. We can also square root both sides to make phantom ones, but I can't show that phantom one garbage to you yet. It's coming though. All right, so every positive number has two square roots because, for example, like we've seen, I'll change the number though, the square root of 25. What two numbers multiply together to get 25? 5 would work, but also -5 times -5 is also still a positive 25. So find a square root is the same as, please find the side length of a square with the area of a square, from the area of a square, from the area. So you have the area, find the side length of a square. Again, it's what number multiplies by itself to get us that value, which is why we don't usually include the negatives, because it really is a side length of a square. Also, I still assume you don't care about this crap. Find the square root of, and this is this is the square root of 81, so it's kind of redundant there. But again, what number times itself is 81? We're just looking for the positive value there. Boom, it's 9. Call it good. All right, for a square root like this one's going to be irrational, and it's going to look like garbage. How do I know that? Because I put it in the calculator. There's other reasons, but the calculator told me. So for those of you wondering, how do you put this in the calculator? Well, you push this button, and this is a square root specifically. So we're looking for the second button first, because we got to apply the square root. So I push it, and then immediately to the left of 7 is what we call the x squared button. But above that, you'll notice it shows the square root symbol. So you push x squared, and then on your calculator screen, it shows the square root symbol. It's telling you, you want the square root? Here it is. Then type in this value, so 0.008, and then push enter. Let's see what we get, 0.008, enter. Yeah, it looks as much like garbage as I thought it was going to. But the decimal shows me 0.089442719er. And just remember, this number repeats. It doesn't repeat. It goes on forever and ever and ever, but never repeats. So that's pretty much all you got to do for this one. Just, I mean, on the assignment, it just may have you round it. So probably to the, I'd say 100th probably. So you should end up with something like 0.09 on this one. And that's all they want on this. So before I botch this up, you could change this into a fraction and then do some simplification. But we're not ready for that stuff yet. So this is all it wants for now is just, can you change this into a decimal? And again, that's using the calculator like we did. And then you get this decimal. That's all it really wants. So this one, just so I don't make the same mistake as I did on that last one, I'm just going to put this in the calculator. So the square root of 0.25, enter. Boom. 0.5. Let's call that good, because that's what it wants on the assignment for this one. All right, like we saw a couple slides ago, it is possible to take a fraction and then separate it into numerator and denominator into their own separate square roots. Now, the reason why this should happen is it should have come out fairly clean, like this one is, until we do a little bit more simplification, okay? Like 9 and 64 are perfect squares, so they simplify into regular whole value bases. But this strategy is good, like you've seen. Well, I guess that probably wasn't a great example, but whenever you see perfect squares in the fraction, generally means that it's going to come out as a clean fraction as well. Like this set right here. Okay, you know, we got square root of 1/4, which really just, again, it just separates the two. Square root of 1 over the square root of 4, both of which are perfect squares. The square root of 1 is 1, and the square root of 4 is 2. That's what we want. Okay, but again, this goes back to that principle of being able to separate them if you need to. So this one as well, remember the negative's on the outside, right? So it's just a negative fraction. Then you take the square root of 1 over the square root of 4, and then it's the same idea, but now, again, it's just that the fraction is negative. Square root of 1 is 1, square root of 4 is 2, but now it's a negative 1 over 2 this time, because the negative was on the outside. Like we've seen, though, if the negative was on the inside of that square root, then it would have been a not real solution for now. Eventually we will find those, but right now we just say they're not real. But this is the way this should go. If you ever see these, and yeah, these ones are coming out clean. Eventually they will not, and we have to simplify those, but you have a tool to do that, which we will show you later. Square root of 25 over 16. Well, just separate that, okay? So you got the square root of 25 over the square root of 16, both of which are perfect squares. Square root of 25 is 5, and the square root of 16 is 4. That is all. Now, the other way to do this is on the calculator, which I mentioned. So, a couple things, right? To access the square root button, you got to push the second. And then one button to the left of 7 is the x squared button. So that would give you the square root symbol. But then you're going to type the n over d button. That's 3 buttons above 7. And then you can actually just type in the fraction. Okay, so then you type in 25 over 16. 25 over, so you go down and then push 16. Then push enter. And it will tell you you got 5/4. So it ends up being the same thing. The other thing it's going to ask for on this assignment is the domain of the root functions. Just remember that the radicand always has to be greater than or equal to 0 if the index is even. So you can't have negative radicands with square roots specifically, right? Because if you take the square root, let's say of negative 100, well, there's nothing that I can multiply it by itself to get negative on this one. So this one we would have to say is not real, okay? Now, what this also means is that when you see the square root of something that has an x inside of it, and you know there could be more to it, like x plus, I don't know, x plus 5x, then what we're saying is that in the domain, again, this is just for the domain, the inside of that square root, x plus 5x, it must be greater than or equal to 0. That's what we're saying. Then you solve that inequality for x, and that tells you the domain. Of course, we're going to look at these with interval notation as well, so be ready for that. And since everyone loved it so much, here it is again. So 4 different parts on this one, but they gave us the individual function up here. T of x, I don't know why it's not f of x, but either way. Okay, so T of x equals x minus 6. So that means right here, this would have been the square root of x minus 6. But it now tells us that the x is 1, right? So I go in and I say, well, my x is 1. And that would give me then the square root of 1 minus 6 is negative 5. But now the inside there is a negative. This negative of the square root of the negative there makes this not real. So what did it say? Find if the value is in the domain, then compute the functional value. This one's not in the domain. because it gives us a not real value.
So it's not.
Well, we're going to keep doing this for all 4 parts. So this one right here, again, we have a value of 8 instead of, because it was x minus 6, but now we'll replace that x with 8. Now 8 minus 6, this one's going to be okay because this ends up being the square root of 2. And that one's okay. In fact, this is really all they want in the box. So when you put this into the box, like if you click on the box, it pulls down that drop-down menu, and then you can just click the square root. Otherwise, I think you type in SQRT, print, yeah, and then it gives you that. But it gives you the button option on the assignment as well. Next up, T of 3. I think some of you guys know where this is going. But right now, it's x minus 6, right? But we're going to take the x and replace it with the 3 because it's T of 3. So replace the x with 3, and then you get the square root of negative 3. But again, it's the square root of a negative, so this one not real, so it is not in the domain. Now this next one, it's x plus h as our, I guess it was x minus 6, right? But now we're going to take the x and replace it with x plus h. So the x that I have right there is replaced with what it's t of, and that's x plus h. And as funky as that looks, it's okay. That is all right. So find the domain in interval notation as an inequality. So remember on these that I don't care about that -1 right there. All I care about is this square root business. In fact, I only care about the inside right there, right? So what this tells me is I need that 7 plus 10 times x. This has to be greater than or equal to 0. That is the domain right there. Once we get this as an inequality, we will make it an interval. First, principles of equality, right? So let's get rid of that 7 because we're solving for the x. That's going to 0 that out, drop my 10 x's. And yeah, addition and subtraction principles of equality will not change the inequality, but 0 minus 7 is -7. Now again, this is all in an effort to find the domain.
Why is it greater than?
So finishing the solution here for this one, I don't want 10 x's, I'd really like 1 x, so divide both sides by 10. And we divided both sides by a positive here. You're going to have to remember that because this is x is greater than or equal to -7 over 10. If I divided both sides by a negative here, I would have had to flip it. So the 7 being negative is not what will affect that inequality. It's just the coefficients, which we've seen. Now I said, like I've done before, I like to see a number line, which will then help me with the interval, right? So I know at -7/10, it says it could be equal to that, right? So you'd have a closed circle there. But this one's eating the x, so it would be a number line to the right. So my interval starting at -7/10, which is included, so it's a square bracket, and that line goes all the way to infinity, which is never included. But this, right at the end there, that is our interval for this one. But again, that's for the domain. Now, here's what the domain is also communicating to us, is that if you replace x with -7/10, you can find a value that works there. That would be real. If you did anything more than that as well, all the way to infinity, you would still get a value that works as a, and you could solve for this g of whatever your x is. But again, the number line is communicating the same thing. The moment you go immediately to the left of -7/10, such as -8/10, then you would get a not real value from the square root part of that. Right, the domain of this function in interval notation, it gave us this little table right there. You can ignore that for now. We'll come back to it, but right now just ignore it, okay? Because we just want to focus on that interval. So we look on the inside of that radical, the square root, which is x minus 3, right? Well, if we could get that to be greater than or equal to 0, then we know we can get real solutions. So again, this is all in an effort to find the domain. Well, only one principle of equality needed to solve this. I'll just add 3 to both sides there. That's going to zero that out, drop my x, which is now greater than or equal to 3. That's the inequality, but we want the interval, so add 3 there. Again, x could equal 3, so it's a closed circle, but it's eating the x, so that goes to the right, which tells us the interval starting at 3, which is included, also goes all the way to infinity. Again, this is for the domain. So any value, including 3 and up, would give us some kind of real value from the function. Now that we have that, let's go to the table. So, if this is saying f of 16, by the way, so instead of it being the square root of x minus 3 there, we now say the x is 16. So replace the x with 16, and you get the square root. 16 minus 3 is 13. Now, if that could be simplified, or if it was a perfect square, we would, but it can't, so it's done. Same thing is going to work for this one. Again, that's f of 5 is really what it's asking for. So we're looking for the square root of x minus 3, but we now have a value to replace x with, which is 5. And that would be the square root of 5 minus 3, which is 2. And that's the one we want there. Now, we did see this as well, but you can take factors on the inside of a radical and separate them into their own radicals. So if you saw something like this, square root of 81 times x to the power of 2, you can separate it into 2 separate factors on the outside as well. So then you got the square root of 81 times the square root of x to the power of 2. How do you get 9x? Because the square root of 81 is 9. And 1 times itself would be x squared right there. It's just x. So that's how we get the 9x. So you see some usefulness right here if you can separate it. The problem is what they're going to do is give us non-perfect squares sometimes. In which case we have to kind of do the separating ourselves. Well, I think we get into that later actually. So this one, all right? We got square root of 121 times x to the power of 4. Let's make that bigger. So I'm going to separate them, okay? So I'm going to make this the square root of 121. And then I'm going to multiply it by the square root of x to the power of 4. Boom. Well, the square root of 121 is a perfect square for 11. That would be 11 times 11, and then I would multiply that by, that's x to the power of 4. What times itself is x to the power of 4? It's x squared. So in other words, we would look at that as kind of like x squared squared, but taking the square root of that garbage. Now I'm leading on to something else as well. That just ends up being x squared. Another way to do this, which you may have seen before, is that you can separate that, right? So x to the power of 4, you could have made x to the power of 2, square root of x to the power of 2 times x to the power of 2, the square root of x to the power of 2, both of which are x. So this would be x, this would be x, and x times x is x squared, which we have shown right there. So that's the one we want. Okay, so this is leading on to more stuff, which we're going to see later, but a square root and a square like this are kind of like how you undo each other. It's kind of like how addition undoes subtraction, or how multiplication undoes division. So those two essentially, I don't want to say cancel out, because essentially they're a phantom one, and then we're just left with whatever was left on the inside there, x minus 15. That's all we want on that. So the square root and the square roots and squares get rid of each other right there. So another way to look at this, what times itself is x minus 15? Well, x minus 15 is, and we know that because it shows, it gave us 2 of them multiplied together. We just want, again, it's a perfect square for x minus 15. Yeah, so this one actually came in very nice for us, right? Because what they end up doing, not that I saw in this assignment, but later on, just to make sure we remember that factoring is one of the things we've learned, they'll make this x squared minus 30x plus, I think this one's 225. And then this factors in, it's a perfect square trinomial for x minus 15, right? So squared, and then you square root that, and then you get this, okay? So again, they're not giving us this right now just so we know, hey, look, if you got a square root and an exponent of 2, they essentially undo each other. Just take whatever's on the inside of those parentheses and call that your answer. So finding a cube root is the same as finding the side length or edge length of a cube if they give you the volume of that cube. Why would you have the volume without the side length? I don't know. Or why couldn't you just measure it? I don't know. But in math, that's the way we're looking at it. And that's what cube roots do. Okay, they give us the side length from the volume of a cube. Now, the nice thing about cube roots is they can be negative because you have a number being multiplied by itself 3 times. So in other words, I could take the cube root of negative 27 right here. This one's okay. This one is okay because what number times itself is negative 27? It's negative 3, and that's okay. Negative 3 times negative 3 times negative 3 is still negative 27. It's 3 negatives. It makes the answer a negative. That's all right. Again, we can't have negatives on the inside if it's a square root or if the index is even. Then we cannot. All right, it says evaluate. I'm just going to simplify it because, well, I guess we can evaluate. It's a cube root. So right now, what I'd like you to do is just ignore the 8. Don't even worry about it. Just look at the cube root. You got to be careful on this. Some students say it's 8 to the power of 3 times the square root of negative 8. No, this is 8 times the cube root of negative 8. So just look at the cube root of negative 8. So what times itself is negative 8? This would be negative 2, okay? Now we need that 8 in the front there. So I would have 8 times negative 2, which is negative 16. Is there a nice way to come up with this negative 2? Sure. Put in the cube root of negative 8 in the calculator and then push enter. So here's how you're going to do it. Okay, for these calculators that we have, the TI-30XS multi-view, type in the cube root. Well, I'm going to type the whole thing in, actually. So that would be 8, right? You're going to type in an 8. Then you need the cube root. So if you're going to type in a cube root, you have to start with a cube. Oh, crap. That means I have to multiply, by the way. So push multiply. That's multiply, not an x. And then type in 3, because we're going to get the cube root. I'm telling the calculator I want the cube root, right? And then you push second. And then remember that exponent button, this one? That's the cube, that's the root, nth root button. And you can see right above it, it shows xth root, like this. So 8 times 3, second caret button, and then just type in negative 8, and then push enter. So negative 8, enter, boom. And it gave me already the negative 16. Now the work was nice, right? It was fun. We enjoyed it. But the calculator's fun too, so get the same answer either way. This is leading into other things, but it's good stuff because this takes us back to exponent rules, right? If you see parentheses like this, we know we're going to be multiplying the exponents. So take your 11 exponent and multiply it by 2/7. We want this exponent as a fraction still. So you can just type in 11 times 2/7 on the calculator, boom, 22/7. That's all we want on this one. Now, what is this telling us? It's telling us something else. We haven't seen a lot of fractions in exponents. So we need to start that, though, because we're going to start seeing fractions in the exponents. Now, what the heck? Because we're going to see this in the next lesson here. But this is actually x. Let's change the color there. It's x to the power of 22, but it's the 7th root of that. You don't have to understand that right now because we're going to see that in the next lesson. But this is the one that we want for now. This is all in a lead up to show you that you can have fractional exponents as well. That goes back to this one right here. So it used to be x minus 15 to the power of 2. Remember that, what I had right there? But the square root is like that to the power of 1/2. And then, well, how do you get, see, you got, yeah, that'd be 2 times 1/2 there, which would just leave you with x minus 15. If you want to show the parentheses to the power of 1, that's fine. But I prefer to see it like this because it makes me feel good inside. So there we go. Again, this is all in the lead up to the next lesson, which we're going to see.